Hi everybody, this is Dr. Bricker here with a video for Chapter 20, Part 2. So I thought we could start with an example problem. 2.1 gram honeybees each acquire a charge of plus 23 picocoulomb. So pico means times 10 to the minus 12th. SI unit, just a small amount of charge here. As they fly back to their hive, as they approach the hive entrance, they are 1 centimeter apart. What is the magnitude of the repulsive force between the bees, and how does this compare to the force? How does this force compare to their weight? Okay, so in Chapter 20, we've been using Coulomb's force law to figure out the force between charges. So here it's two honeybees that each have a charge of plus 23 picocoulomb, so they're like charges, so the force is repulsive. So we have F is equal to K Q1 Q2 divided by the distance between them squared. So remember, K is just a constant. 9 times 10 to the 9th newtons meters squared over coulomb squared. And we know the charges, both of them equal to each other. And it's given in the problem. I'm not going to rewrite it. Just remember that's 23 times 10 to the minus 12th. And then in the formula, R is the distance between. So here we have 1 centimeter. You got to change that into meters, so divide by 100 because there's 100 centimeters in a meter. So the distance between them is 0.01 meters. And then we have everything. You just have to plug it into this formula. Okay? So that's how you get the electric force. And then to get the actual weight, this is equal to m times g. So this problem illustrates the force of gravity versus electrical force. And you might be surprised to see how large or small each of them is. So the mass here, it's 0.1 grams. You have to put it into kilograms. So you got to divide that by 1,000. Okay, so I'll just leave that part for you as well. Just remember mass 0.1 times 10 to the minus third kilograms. Okay, very good. So sort of a straightforward electrical force problem. So related to this idea of force is electric field. In Physics 220, we had gravitational field. We thought of it as 9.8 meters per second squared, but I showed you in part 1 of chapter 20 that you could actually write it as 9.8 newtons per kilogram. And that would be close to the surface of the Earth constant. So if you knew the mass, you could multiply it by 9.8 newtons per kilogram, and you could figure out the force. So the point of knowing the gravitational field is you could figure out the weight force. The point of the electric field idea is if you know the strength of the electric field and you know how much charge you're putting there, you can figure out the force on a charge in an electric field. So it's the same idea. So the field model explains how the force due to charges is transmitted through empty space. There's nothing really there, but it's just a way to think about it. So here you see some pieces of metal lined up in an electric field. This actually turns out to be an electric dipole. These are, let's see, the figure shows a shallow pan of oil with grass seeds. Positive, negative wires touch the oil, and this pattern emerges. So you induce charges, induce a situation of separation of charge on the grass seed, so you induce that to happen. Put an electric field in the oil, and you get this arrangement. Okay, so a similar idea to gravitational field. So in the force model of the electric field, that's what we were talking about previously, the positive charge is attracted to B here. The thing about electricity, it's a little trickier than gravity. So a gravitational field is always attractive. With electricity, you could have attractive or repulsive. So it says down here, analogy to G. We've seen this before in part 1. G, 9.8 newtons per kilogram. And the gravitational field would look something like this, pointing down towards the Earth. So if you put a mass in a gravitational field, it would experience a force. So let me just put a mass here. It has mass, it's in a gravitational field, it would experience a force in the same direction as the gravitational field. Electricity is just a little trickier because we could have repulsive or attractive forces. Okay, so a group of charges, which we will call our source charges, alter the space around them by creating a gravitational field. So, electric field. You could think about it like a gravitational field, though. So you have mass, there's a gravitational field around you. The Earth has mass, there's a gravitational field around the Earth. The Earth has a lot of mass, so you actually could experience it. I mean, theoretically, you have mass, you're attracting other objects that have mass. That force is just really, really small. The Earth is really, really large, comparatively speaking, so mass that comes close to the Earth actually feels that force. Okay, so in the electric field idea, if you put charge in an electric field, it's going to experience a force. Just like if you put a mass in a gravitational field, it's going to experience a force. Okay, so if you just have one point charge, you could figure out the electric field from this equation. So if you took the force that it experiences divided by the charge that you put there, you get the electric field. Probably a better way of thinking about this formula, this is the way I think about it. F is equal to Q times E. So this is more of a useful way, in my opinion. If you know the electric field and you know the magnitude of the charge, you could figure out the amount of force. So the unit of electric field you can see here is a Newton per Coulomb. Just like if you knew the gravitational field and you knew the mass, you could figure out the force. So that's the analogy, that's the point I'm trying to make here. So when it says capacitor example, this is what a capacitor would be. There's a couple of charged plates. So this plate is positively charged, so we've removed electrons from it. This plate is negatively charged, so there's an electric field between the plates. And the electric field goes from the positive side to the negative side. So if you were to take a charge, put it in this electric field, it's going to experience a force from the formula that I have written up here. F is equal to QE. Okay, so we'll use this example a lot. The capacitor gives us a uniform electric field. It's constant, pointing from the positive side to the negative side. So the force on this positive charge would be this direction. And if you can think about it this way as well. This positive charge does not want to be by the positive plate. It does want to be by the negative plate, so the force would be the other way. Now the tricky thing about electricity is if this is a negative charge and you put it in this electric field, the force on it's going to be the opposite direction of the electric field lines. So a positive charge in an electric field, the force is along the electric field lines. A negative charge in an electric field, the force is the opposite direction. Okay, good. So that's a good place to start. It's a good way to think about it. Here are some typical electric field strengths. So inside an atom, all the way like 100 billion newtons per coulomb. Needed to have a spark in the air. This would be kind of like, lightning. About 1 million newtons per coulomb. Objects charged up, pretty good amount here. 10 to the third, all the way up to 10 to the sixth. The Earth's field near the Earth's surface, something like around 100 newtons per coulomb. Inside a wire, not very much. That might be a little bit surprising, but a wire, there's a lot of charge carriers that are free to move, so you don't need a huge electric field to have an actual circuit running. Okay, just so you have an idea of these strengths. So you can use a charge as a probe to determine whether an electric field is present. So if you put a charge at some point, it experiences a force, well, there must be an electric field there. Just like if you put a mass somewhere, it experiences a force, well, there must be a gravitational field there. So positive charges, again, point in the direction of the electric field. Negative charges, the force would be the opposite direction of the electric field lines, as you saw from the capacitor example. Okay, so as I said earlier, the Earth has mass, it has a gravitational field. I have mass, I have a gravitational field. Charges on their own have electric fields. So you can use a second charge to probe the electric field. So what is the electric field at this point? Well, because of Q. So what is the electric field here because of Q? Well, what would happen if you put a positive charge at this point that I've circled? If you put another positive charge here, called Q prime, the force would be away from Q. So this charge, Q, has an electric field. We're probing what the electric field looks like by putting Q prime in it, and in doing so we see there's a force on it. So the electric field lines, because of a point charge, point away, as you can see in this little example. Here's the magnitude of the electric field due to a point charge. K, the same K that we had before, Q divided by R squared. And for a positive charge, the electric field points away everywhere. And for a negative charge, the electric field points towards it. Now, in this little picture here, if I think about these both simultaneously, we'd have an electric field that looks like this. This is actually an electric dipole. So what would happen if you put a positive charge somewhere here in the electric field? If you were to add a positive charge here, it would have a force this way. This formula gives you the magnitude of the electric field because of a point charge, and then you just have to know positive charge, it's away, negative charge, it's towards. And you can have a whole collection of charges. Here's an example. The electron in a hydrogen atom orbits the proton at a radius of 0.053 nanometers. You might recognize this number. What is the electric field due to the proton at the position of the electron? Okay, so the proton in the hydrogen atom produces an electric field. What is the strength of that electric field where the electron is located 0.053 nanometers away? Okay, so we've got our formula now. Electric field, KQ divided by R squared. It just so happens this is a proton, so we know that the charge is the fundamental charge, 1.6 to the minus 19th. Here's the distance away. 0.053 nanometers is 5.3 to the minus 11th meters. Square it, and you get a really big electric field, as you saw from the little chart of different electric field strengths. Okay. So that electric field points away from the proton. There's a negative charge there, so the force would be towards the proton on the electron, which, as you know from circular motion, it should be. Okay, excellent. That's kind of a synopsis of what I've said. So a positive charge, electric field lines point away. The farther and farther you get from the charge, the smaller and smaller the electric field is. And you can see that in this sketch too. That's smaller than this because we're farther away. Okay, negative charge, electric field lines point towards. And again, the farther you are from the charge, the smaller and smaller it goes. The electric field is proportional to 1 over R squared. So if you're twice as far away, the electric field strength would be 1/4 as much because you're squaring the factor there. Okay, at which point is the electric field stronger? Point A or point B? Well, the difference between point A and point B is point A is closer, so the electric field is going to have to be stronger. Okay, good. Let's take a look at this one. All charges shown have equal magnitudes. For case 1 through 4, is the electric field at the dot to the right, to the left, or 0? Okay, so we've got to look at all of these different 4 cases. These are all separate from each other. So in case 1, the electric field at this dot, so I'm looking at case 1, the electric field at the dot because of the negative charge would be this way. Whoops. At the dot because of the positive charge, it would be this way. And notice I drew the contribution from the positive smaller because it's farther away from the dot. So the net amount would be this way. For the second case, we have away because of the positive charge at this point where the dot is, towards, because of the negative charge, this one is winning, because to the right is bigger than to the left. To the right means from the positive charge, to the left means from the negative charge. Point 3 here, because of the closer one, electric field is away. Because of the farther away one, it's still away because it's positively charged. So the net result is to the left. Oh, this might be kind of an interesting one. At the dot, I'm looking at case 4, at the dot, because of the negative charge, it's this way because it's toward a negative charge. Because of the right negative charge, it would be this way. This one actually cancels out, and we get 0. So let's see, we have left, right, left, 0. Let's see if that's correct. Left, right, left, 0. Okay, very good. Lots of information on that slide. So let's just look at case 1. We've got 2 charges, the plus and the minus, and we're looking at the electric field at the point of the dot. So for a second, pretend the positive charge is not there. The electric field at the dot, because of the negative charge, is this way. Now pretend the negative charge is not there. Which direction is the electric field at the dot? Because of the positive charge, and it would be this way. I'm just kind of giving you a summary of what I've done. So we've got a contribution from the positive and the negative charge at the dot. You add them together, and you're left with to the left. Okay, and the same idea for the other ones. Some applications of the electric field. Parallel plate capacitor is an arrangement of 2 electrodes closely placed together, charged equally but with opposite. So an electrode is a conducting plate. And we kind of saw what that looks like before. This is a way of getting a uniform electric field. Now, I know you probably have a cell phone, you're looking at your computer, you're using capacitors right now. They're used for a lot of different applications. Storing charge, they're used in communications for something called RC circuits. So lots of different uses for capacitors. So Physics 221, we do electricity, magnetism, etc. You can take whole classes on just circuits, whole classes basically on RC circuits, get degrees in electricity. So we're sort of doing this for, electricity for 3 or 4 weeks or so. So there's a lot more information out there. We are sort of getting an intro to this stuff. Okay, so chances are you're using a capacitor in some way right now as you're listening to this. So here's a couple of circular capacitors. Plus Q on one, negative Q on the other. Electric field between them, going from the positive to the negative. And they're separated by a distance D. They have a plate area called A. In a minute, we'll have an electric field due to a parallel plate capacitor. So we know the electric field due to a point charge. In a few minutes, we'll have the electric field due to a capacitor. Okay, so inside a parallel plate capacitor, the horizontal components of the individual fields cancel out. There's a part to the left, part to the right. What they're trying to do here is look at the electric field at, say, this point because of all of the charges. There's electric field at that point because of this one. There's electric field at that point because of this one, this one, this one. Those aren't minus signs, by the way. Let me make those into arrows so it's not confusing maybe. Arrow, arrow. There's an electric field up at that point because of all these charges. And what you end up getting is the horizontal components cancel out, and we're just left with the component that goes straight across. So we're talking about the electric field inside the capacitor. Once you start to get to the edges, you get some fraying going on. But right between the plates, relatively speaking, the electric field is constant. Those are the situations that we will actually talk about. Okay. So inside a parallel plate capacitor, electric field at every point is the same direction, nice and uniform. In reality, on these edges, though, you do get some fraying going on, so we won't be considering that. On the edges, it would actually kind of start doing this. Okay, but we're considering it to be uniform between. So here's the strength. It's K. Oh, sorry, we're not writing it as K. The electric field is Q. That's just the magnitude of the charge on one plate. So magnitude of charge on one plate. I'll just put one plate. You don't add them together or anything like that. A is the area of one plate. And epsilon naught, that's how it's pronounced, epsilon naught, is the permittivity constant, and it's equal to 1 over 4 pi k. So you could actually write that in terms of k if you wanted to, the electric field strength. It's just a new constant, so you don't have to write 1 over 4 pi k every time. Actually, it would be, the electric field would be 4 pi k q over a. So this is a little bit smaller. But this is the relationship between epsilon naught and k. So 8.85 to the minus 12. If you want to check that out, you could put in k, and you'd see that you get 8.85 to the minus 12. Coulomb squared per Newton meter squared. Okay, so we've got the electric field because of a point charge. We saw that earlier. Now we've got the electric field because of a capacitor. Okay, and we also know the use of an electric field. We saw this the beginning today. F is equal to Q times E. Okay, so we're getting somewhere. We'll be able to do some examples in just a few minutes here. Okay, so the field depends on the charge to area ratio, sometimes called the charge density. So if the charges are packed more closely, the electric field is stronger, right? This is in the formula. Okay, so the plate separation is small compared to their size. That's where the formula actually comes from. All the problems that we do will be that situation. The shape of the electrodes isn't relevant as long as they're close together. Usually it's circles like we saw, or maybe squares. You know, just a square couple of plates. Now, if you look at your, if you've ever looked at circuits before, they look like cylinders. So there's actually cylindrical capacitors as well. But we'll be looking at these sort of capacitors. So it looks something like this. And inside, which you don't see, there's another cylinder. And then there's a couple of leads. So if you've seen something that looks kind of like this, if you looked at a circuit, and it's measured in, you might see a unit called a farad on there. That's probably a capacitor, a cylindrical capacitor. Mostly we'll be dealing with just the kind we've mentioned already, parallel plate capacitors. Okay, here's an example. Long highway tunnels must have air cleaners to remove dust and soot, as you can imagine, from cars and trucks passing through. In one type, known as an electrostatic precipitator, air passes between oppositely charged plates, as in the figure. Okay, so there's a couple of plates. Charged particles move between the plates. There's an electric field. The charges are moved from one plate to one plate or the other plate, filtering them out. So we see the size of this, 38 centimeters, so 0.38 meters. That's the dimension. The separation is 0.9 centimeters. Now, if you remember, the electric field, due to a parallel plate capacitor, doesn't depend on the separation. It depends on the area. So many times problems will give you this dimension, and when they're looking for electric field, and you don't even actually need that. Okay, so we've got all the information. The large electric field between the plate ionizes the dust, so charges up the dust, removes electrons, which then feel a force due to the field. So the particles are charged up. Charged particles in an electric field will experience a force. We want to know what is the electric field between the plates. Okay, so we've got the formula for that. Before that, let's take a look at this. We know the charges. We know one side, and it's a square, so we can figure out the area. Actually, looking at this a little closer, it's not actually a square. This is 38 centimeters. This is 20.6 centimeters, so it's not quite a square. It's more like a rectangle, but we can still find the area, one side times the other side. Okay, so the electric field charge on one of the plates, the magnitude of it. Okay, good. Epsilon naught, that's just a constant. And then the area. You can get the area, this dimension times this dimension. Make sure that you have it in meters. Actually, this should be meters squared here. Okay. Put it all together, you get 7.8 times 10 to the 5th newtons per coulomb. So pretty big. It's almost large enough to be 1,000,000 newtons per coulomb, and that's the case where you'd actually get a spark. Not quite there yet, though. Okay, good. So charged particles entering this electric field would experience a force and be driven to one side or the other, depending on what charge they have. Okay, good. The electric field is to the left because it goes from the positive side to the negative side. So you saw before that this electric field strength would create a spark in air. The field here is a little bit smaller, so not quite enough to make sparks fly. All right, excellent. So a cell membrane is an insulator that encloses a conducting fluid that's surrounded by it's conducting fluid surrounded by another conducting fluid. So the membrane really acts like a capacitor because you've got a separation of charge. So when a nerve or muscle cell is stimulated, the cell depolarizes, which means switches polarity. When the charge balance is later restored, the cell repolarizes. So if you've ever seen an EKG, you see like a positive part of the chart, then a negative part of the chart, and then a positive part of a chart. That's really what's going on here. Okay, so we got this capacitive effect going on. When people try to, analyze what's going on with the human body, you have to come up with some sort of models to do this. So capacitors come into play many different times. Okay, and as you can see there, separation of charge. Okay, kind of a synopsis of what I've said. Okay, because there's a separation of charge, we also have an electric field, and you can see that here as well. So an electrocardiogram measures the changing field of the heart as it actually beats. So if you've ever had one of these, electrocardiogram, that's really what's going on. Okay, here's a quick check, 2027. Which of the following is the correct representation of the electric field caused by two positive charges? Okay, so remember, for positive charges, the electric field goes away all over the place, right? And I'm just giving you a couple of the lines here. You saw a better picture drawn before. Down here it would be this way. I don't want to mislead you. It's the same size as here. Okay, so always away from a positive charge. It can't be this one because, look, you got electric field lines going towards it. Here, you got electric field lines going towards the lower one, so it can't be this one. Electric field lines for positive charges always have to go towards them. Or sorry, away from them. It can't be D either. Here you have electric field lines going towards. This would be D would be correct if it was actually, if those were two negative charges. So it's got to be C. Electric field lines always go away from positive charges. Okay, here right in the center, actually the electric field would be 0 right here between them. They are canceling out. Okay, good. So choice C, always going away. So these examples will be on another video I'm making called Homework Help 1 video. So conductors and electric fields. So here's a few things about conductors. And remember, right now we're talking about electrostatic equilibrium where charges are not moving around. So for a conductor, the electric field inside a conductor in equilibrium here has to be 0. If it weren't 0, if there were an electric field inside a conductor, there's charges there, they would be moving around. And what we have here is a situation where charges are not moving around. So all the charge has to be on the outside for that reason. Okay, so all excess charge is on the surface. No electric field inside. So if you've ever been enclosed in some sort of metal, it sounds a little ominous, but say you're in a room or something that has a lot of metal in it. the electric field is really approaches zero there. It's hard to get a signal. In my house, I've got metal siding, and I've got an antenna, which I get stations from both South Bend and Chicago. So I'm picking up the electric field and magnetic field from these stations. I can't just have a regular antenna on the first floor by my TV because it's being blocked by having a conductor around it. I've got to place my antenna actually in the attic away from the metal, and I can get an electric field that way. Okay, so there's something called a Faraday cage. If you take a radio and you put it in just a cage made out of chicken wire, you won't get any signal because the electric field doesn't go through that. It just takes like even chicken wire works there. If you take the radio outside, then you outside of the cage, then you actually have a signal. So if sometimes you can't get a cell signal, maybe you have a lot of metal around you blocking the electric field being zero inside a conductor. Okay, so that's sort of a consequence of this. The electric field always points away from the surface then. No part of this electric field can be this way. If it were, the charges would be moving. So you can't have the electric field being that way. It has to point perpendicular to the surface, and then charges are not moving. Okay, so the charges go to the surface and they spread out because they do not want to be close to each other. So this is a little misleading. I mean, they have a bunch of positive charges here. In reality, what you probably would have is electrons, so you'd have negative charges there. Okay, so the electric field right at the surface of a charged conductor is perpendicular for the reason I just explained. Now, if you have an enclosure inside here, like a hollow spot, the electric field is still zero here. So a conducting box, as I said, can be used to exclude electric fields, something called screening. So metal walls are ideal for screening. If you're doing sensitive research where you want to avoid any outside interference, you'd have the walls maybe lined with some sort of metal meshing or something like that to block out extraneous electric fields. In my case, where I just want to have a little antenna by my TV, it's kind of a pain. I can't get a signal, so I have my signal blocked. But I've corrected that by putting my antenna in the attic. Okay. So although any excess charge of a conductor will be found on the surface, it may not be uniformly distributed. Pointing surfaces, just because of the geometry here, have more charge. Okay, good. This is actually the idea behind a lightning rod. So a lightning rod looks something like this. And the idea is you're not trying to attract lightning, so this would be by your house or something. This is a lightning rod. You get a bunch of negative charges here, and you're not trying to get lightning to hit your house. You're trying to have lightning not hit your house. So if you get a whole bunch of charges accumulating here at this pointy tip, they could bleed off into the moisture in the air, and you can decharge your house. You don't want your house to be charged up when a charged cloud or whatever it is comes by, and if you get an electric field greater than 1,000,000 newtons per coulomb, there's a chance your house could be hit by lightning. So you put this lightning rod here to get charged to go away from your house, and then you don't have an electric field between your house and something else. Okay. Oh, as it says here, lightning rod has sharp points so that if the building is beginning to accumulate charge, meaning a lightning strike is imminent, the large field develops at the tip of the rod, ionizing the air and removing the electrons from the rod. It's to prevent a lightning strike. Okay, good. That's probably a better summary than what I said. So forces and torques in electric fields. So again, we saw that this is really the use of this idea of electric field. You know how much charge you put there, you can figure out the force. I always write it with the absolute value because you don't know the direction of the force. Really, you have to know what kind of charge you have and which way the electric field lines are going. So I always just write it like this. So here's an example. Under normal circumstances, the Earth's electric field outdoor near ground level is uniform, about 100 newtons per coulomb. We saw that in the chart before. Directed down. So if it's directed down, oops, not sure what happened there. Okay, again, so if it's directed down, you could kind of think about it. This is a capacitor, right? This would be the negative side. You could pretend like this is the positive side. Then the electric field goes from positive to negative. So the earth is down here at the ground, so it's negatively charged. Up here, you have something that's positively charged. It's taken me a while to write all these positives. There we go. Okay, so we've got this. We know the strength of it's 100. What is the electric force on a free electron in the atmosphere? What acceleration does it cause? Okay, so the electric field is given. They tell us it's an electron, so we know the charge of an electron, negative 1.6 to the minus 19th coulombs. So we know the electric field, we know the charge. Because it's an electron, we could figure out the force, and then from Newton's second law, we could figure out the acceleration. Okay, so that's in a picture of it. The direction of the force is, as you see there, it would be towards the positive plate, right, from the previous slide. The direction of the force on a negative charge is opposite the direction of the electric field lines. Okay, so here's the magnitude of the force, 1.6 to the minus 17th, and it's upward. I did this whole capacitor example just to give you an idea. Okay, there's an electric field. Which way is the force? You could just memorize which way the force is, opposite direction of the electric field lines. Or you could think what might actually make an electric field that looks like that. That's why I drew in a capacitor. That's one possible way of thinking about it. And then the negative charge is attracted to the positive plate, repulsed by the negative plate. However you want to think about it. Okay, the acceleration from Newton's second law, F is equal to ma. So A is F over m. There's the force. Now, not a very big force, but again, the mass is really, really small. So 1.8 to the 13th meters per second squared. So a really large force. Or really large acceleration, I should say. Small force, relatively speaking. Really big force to an electron, though. Okay, so this everyday field produces extremely large accelerations of a free electron. Forces and accelerations at the atomic scale are quite different from what we're used to seeing for macroscopic objects. Okay, and you might have done this in some other classes. To get the colored lines produced by gel electrophoresis of a DNA sample, you put the samples of DNA into the solution, then cut the DNA into fragments by enzymes, so you get pieces of DNA. In the solution, the fragments have a negative charge. So in the picture, these fragments have a negative charge. You put them in an electric field, and actually this was one of the first slides we saw in this chapter. You put them in an electric field, they're negatively charged. The force on negative charges in this picture, the force is going to be to the left. So drops of the solution are placed in wells at one end of the container, and different fragments have different sizes and migrate at different rates. So they spread out according to that, and get a unique display from that. So different pieces experience force, but some of them are larger, spread out at different rates, and you get a picture that might look like this. Okay, cool. So that's related to biology and chemistry, really. Okay, so drag forces cause some fragments of different sizes to migrate at different rates, and you get this picture. The so-called genetic fingerprint. So two identical samples would produce the same picture, different samples, different patterns. Here's another example we can take a look at. Electric field is 200,000 newtons per coulomb to the right, causes a 2-gram ball to hang at an angle. What is that angle? Okay, so if you actually did this, you would get this picture. We can take a look at this problem too. Free body diagram is really needed for this one. So what's keeping this? What are the forces on this actual ball here? let's do the free body diagram. So you got this electric force to the right. I'll just call it force electric. You got the weight straight down, and you got tension this way. Okay, so all these forces are balanced. Whatever's to the left has to be equal to whatever's to the right, and in the picture you can see what the angle would be. So in terms of left and right forces, you're going to have tension in the X this way. That's balancing the electric force. And then you've got tension in the Y this way. That's balancing mg. And then in the picture, you see what theta is. So this is back to being theta over here then, right? Let me, maybe I'll draw it on here. Ty, if that's theta, this is theta. Here's Tx, here's mg, and then here's the electric force. Okay, maybe that looks a little bit better. Not drawn to scale. Okay, so from physics 220, we know that Tx has to be equal to the electric force, which is equal to Q times E. Ty has to be equal to mg. Just be careful that mass is in grams. We need it to be in kilograms. So really the mass is 2 times 10 to the minus third if we thought about it in kilograms. Okay, so you can get Tx and Ty from the electric field, electric force part and the mg part. So I'll leave that to you. You have everything to do this. Here's the charge, 25 to the minus 9th coulombs. So you know Q and you know E. You can get the tension in the X. M is given. G is 9.8. You can get that. So that's good. We know all the forces. How are you going to get theta? Well, we'll have to do a little bit of trig. So tangent of theta is equal to the opposite side over the hypotenuse. So then theta is the inverse tangent. So inverse tangent of Tx over Ty. Okay, good. So get those individual forces, Tx and Ty, from balancing forces, and then you can get theta. The larger the electric field, the greater the angle that this would actually hang at. Okay, great. And then I will make another video with the homework hints for 2041 and 2045. Okay, so I usually leave the summaries here for you to take a look at. I'll just say a couple of things about it. So we've got two kinds of charges, positive and negative, and really it comes down to being a fundamental property of protons and electrons. Okay, so neutral doesn't mean no charge. Neutral means equal amounts of positive and negative charge, and you can't get rid of it. It's neither created nor destroyed. Here's Coulomb's force law. So if you have a couple of charges, they have a force on it. Opposites attract, likes repel. The SI unit of charge is a coulomb. And we have a couple of situations where we can figure out the electric field. We saw those today. The electric field due to a point charge. We saw that. Actually, let's see if that's on the next slide. Electric field due to a point charge. We saw that. Electric field due to a capacitor. So we can calculate those. And the use of those is if you know the electric field strength, you could figure out the amount of force. Okay? Using everything from the example that you just saw where that ball was hanging off to the side at an angle, all the way down to DNA profiling. So electric fields are vector items. For positive charges, they're away. Negative, a collection of negative charges, it would be towards, and you could figure out the force. Now, if you have several different charges, you have to add up the contributions from each charge, and you'll see that in the homework in terms of the electric field. That's what this is saying, E1 plus E2. Maybe you have a few charges, you want to know the electric field between them. You'd have to add up the individual contributions. We did that qualitatively today, the example with the 4 different cases. With the homework, you will see some examples where you actually put the numbers in. Okay, and again, visualizing electric fields away from positive towards negative. And here's actually an electric dipole, positive and negative charge. Okay, very good. Any questions, just email me and I will talk to you soon. Bye-bye.